Okay, I'm gonna go ahead and take attendance now, and in the meantime, please start working on today's warm-up. So item number 1, please solve for the system of linear equations using Gaussian elimination. And our system of 3 linear equations is going to be x plus 2y minus 3z is equal to -3, 2x minus 5y plus 4z is equal to 13, and 5x plus 4y minus z is equal to 5. Please use the method that we learned yesterday with matrices in order to solve for the intersection of these 3 planes in physical space. That is to say that the first thing you want to do is you want to turn this guy into an augmented matrix. And then after you have it turned into an augmented matrix, start doing row operations until you can isolate x, y, and z. And just so you know, this system of linear equations has one unique solution. So this isn't a case where you'll run into a no solution scenario. And the solution, I believe, is integer. After that, the other half of the warm-up, I'll show y'all how to do these manipulations in your graphing calculator, which is why we even bothered with the vocab yesterday, talking about row echelon form and reduced row echelon form, because those are phrases that your calculator actually understands. So if you have your graphing calculator nearby, please grab it, because I'll be going over how to enter this stuff in your calculator, and I'll write down some little notes here so that you can have that on the side. Also, please notice that the current homework assignment is due tomorrow, because this stuff is time consuming to do by hand, so I wanted y'all to have a little bit more time to do it right.
Good morning, Mr. Robinson.
Good morning, welcome in. Happy Friday. Okay, let's go ahead and get started, just because this is a time-consuming procedure. And just so y'all know, today after we're done working our way through this, we will have a couple items of notes to wrap up what we were talking about yesterday. No new math, I just want to talk a little bit about how we can look at a matrix and know that we are in one of the weird scenarios, one of the cases that we talked about at the beginning of the chapter, where you could have either no solution or a set of infinite solutions. That's one of the nicest things about working on these types of problems in matrices instead of just using regular elimination. Seeing that it is a no solution scenario or an infinite solution scenario becomes way easier than when you're doing regular elimination. Okay. So the first thing that we're going to have to do in order to solve this system here is we need to write it as an augmented coefficient matrix. Now, when I work on these types of problems, just so you know, to save space, I kind of snake my way down the page. So as I go from step to step or whatever, I'm going to have arrows indicating the logical flow of what's going on. You don't have to lay your work out this way. Feel free to lay it out whatever way is comfortable. So the first thing that we're going to do here is we are going to write out our coefficient matrix. And so all I'm going to do is I'm going to pull the coefficients off of each one of the variables because they're already laid out in row 1 being x, row 2 being y, row 3 being z. And so here's my coefficient matrix. 1, 2, -3, 2, -5, 4, 5, 4, -1. And on the other side, I'll put my constants, -3, 13, and 5. First step's pretty easy. So which 2 digits do we need to target first? What zone of the matrix do we aim at in our first steps to try and zero out so that we can turn this into row echelon form?
Maybe row 2 or column 2 actually. So the 2 and the 4.
The ones in the bottom left.
The values in the bottom left. So that is to say that our initial targets are going to be down here. We want to make this 2 and this 5. We want to turn those into zeros. And then as soon as we turn those into zeros, we also want to get this 4. So we want to get rid of that bottom left corner first thing. And then after we get rid of the bottom left corner, then we can work on getting rid of the top right corner. So the first thing that I need to do is I need to line up all of these x values so that they are eliminatable. So what is a common factor here that I can get to eliminate 1 and 2 and 5?
10 maybe.
10.
Oh, it's not even a maybe, it's a definitely, yeah. We're going to turn this into 10. So I'm going to multiply the first row here by -10. I'm going to multiply the second row here by 5. And I'm going to multiply the last row here by 2. So that we can have -10 and 2 positive 10s so that it's easy to eliminate these 2 values. And keep in mind that there are only 2 row operations, and as long as you are only making those row operations, it won't change the value of the solution. We can take any line and multiply it by a constant so long as we multiply everything in the line, and then I can take one line and add it to another line as long as I add an entire line to an entire other line. So row 1 multiplied by -10 is going to give us -10, -20, +30, +30. Row 2 multiplied by 5 is going to give us 10, -25, 20, and a big number, 50 plus 15, 65. I'm going to be extra careful as we go through problems like these, just because one small error in a previous line will jack up the rest of the problem permanently. So if you ever catch a mistake, please do not hesitate, even if you're only 50% sure that it's a mistake. Are there any questions on that first step, or did I make a mistake? No, looks good. Yeah. Okay, so now what was the point of multiplying by that constant?
The x's can cancel out.
Now the x's can be canceled. So to row 2, I will add row 1. So to this, I will add row 1. And to this, I will also add row 1 so that we can eliminate those 2 x values. And so this is going to become the following augmented matrix. And of course, the first row is untouched by this. We're taking its values and adding them to the other rows, so that doesn't affect it. So this is going to give us 10 plus -10, which is going to be 0. -20 plus -25 will be -45. 30 plus 20 will be 50. And then 30 plus 65 will give us 95. That's our new row 2. And then row 1 plus row 3 is going to give us 0 and -12 and 18 and 40. And that's our new row 3. Are there any questions up through there?
Yeah, Mr. Robinson, shouldn't all the x's be 0?
No. I made all the x's 0, 0, and 0.
Mr. Robinson, shouldn't it be 28 instead of 18?
Oh, yep. Yeah, this right here, right? 28? Yeah. Thank you. Yep, 28. Okay. Any other questions up through here? No? Okay. So what's our next digit that has to go?
negative, actually 4. So the bottom, on the last row, number 4.
-12.
The next digit that has to be destroyed is -12, because that will give us a very clean bottom left corner. So the next thing that I need to do is I need to eliminate this -12. And I actually am extremely limited in terms of what values I have to do that with. We actually have to eliminate this -12 with -45. We cannot do it with -20. Can somebody tell me why not? What would happen if I took row 1 and I added it to row 3?
There would be a -10, like it would go back to what it was in the beginning.
Exactly. It would undo what we did before in eliminating this value here down to 0. So when you try and eliminate this y value, I guess we could call it, since it's in the middle column, you have to do it with -45 so that when I eliminate row 2 with row 3, these zeros remain unaffected. Yeah. So we need to try and line up -45 and 12. Now, we could multiply them together, but that would yield some really, really, really big numbers. So what do y'all think is a potentially smarter way to go about this? Anybody?
Like find a common multiple.
Yeah, but I want to find a small common multiple instead of a giant one. So
So least common multiple. Just the LCM.
Yeah, so what is the least common
With-
multiple that you can find between these two?
Is it 180?
Even smaller.
90.
Smaller. If you notice, all of these values in here are multiples of 5. We can start by taking that middle row and simplifying it down by 5 first. I think that will make it easier to locate a common multiple before we move along. And just so you know, like that's a thing that you can almost always do is take a row and simplify it down. So before we move along, just so that we're playing with smaller numbers, let's take and reduce some of these rows down with some convenient constants. So what's a good constant I can hit that top row with to make all of its values smaller?
10.
10.
Yeah, 1/10. And then this second row, what's a good value to hit
1/5.
this with? Yeah, let's hit this with 1/5. And then this bottom row, all of these are even at least. So maybe.
4th.
Oh yeah, they're all actually. Are they all divisible? Yeah, they're all divisible by 4. So we'll hit all of those with 1/4. Okay. So now we're going to get a new matrix here with some smaller numbers so that we can fiddle with finding common multiples. So that's going to be -1, -2, 3, 3, 0, -9, 10, 19, and then 0, -3, 7, and 10. And now it's nice and easy to find a small common multiple between these two. Just 9, yeah? So I'm going to take the bottom row and I'm going to multiply the bottom row by -3. So now this is going to become -1, -2, 3, 3, 0, -9, 10, 19, 0, 9, -21, -30. And again, the point of this is so that this position is eliminatable. So to row 3, I'm now going to add row 2. And in doing so, row 1 will again be unaffected. So that'll give us -1, -2, 3, 3, 0, -9, 10, 19. And then when I add row 2 to row 3, 0 plus 0 will give us 0. -9 plus +9 will give us 0. 10 plus -21 will give us -11. And then 19 plus -30 will give us also 11.
-11.
-11. Yeah. Okay. So we have accomplished the first part of our goal. We have successfully zeroed out this entire bottom left corner. Is that okay?
Yeah.
So now where are we going to set our sights?
Top right.
Now we're going to set our sights on the top right. We need to turn all three of these numbers into zeros. And just so we're clear, the current form that we're in, this is row echelon form. And the additional work that we're going to do to delete this top right corner is going to get us into reduced row echelon form. So just a quick note, being at this step right here with this corner set zeroed out, this is REF row echelon form. So now, and I'm gonna, this kind of sucks because I ran out of space on the page. I'm gonna multiply the bottom row by -1/11 so that it's easy to see. I'm gonna multiply the bottom row by -1/11 before we move along to the next page, but I'm gonna leave the rest of it unaffected for now.
Mr. Robinson, with this system, are you not supposed to narrow, like, you can't narrow it down to two system of equations with two variables?
We just did that. So when we were here at this step, if you ignore this top line, this is a system of two equations with two variables. This is saying that an equivalent solution to this system is -9y plus 10z is equal to 19, and 9y minus 21z is equal to -30. It's exactly the same. I mean, this equation right here is telling us that what is our answer to z?
-11.
1.
Z is equal to 1. This equation right here is saying -11z is equal to -11, which tells us that z is equal to +1. So the logic of this is the same as elimination. It's just tidier. Now, of course, it's slower because we're like learning it and I'm explaining every step. But if I was to be working on this on my own just to get the solution by hand, I would have been done like 10 minutes ago. The time-consuming part is the voiceover. Okay. So like I said, this gives us -1, -2, 3, 3, 0, -9, 10, 19, 0, 0, 1, 1. Okay. And again, the next things that we are trying to eliminate are these guys. So I have 1 and 10 and 3. Common multiple. Multiply them together.
30.
30, yeah, and there's like nothing simpler just because 10 doesn't have the factor of 3 built into it. And so I'm going to multiply the bottom row here by -30. Oh, I didn't leave enough space to write it here on the left. -30, we're going to multiply this row here by 3, and we're going to multiply the top row there by 10. And so this gives us -10, -20, -30, -30. If I was psychic, I would have left it that way, considering, you know, it was that before, and then I divided
Wait,
it by
Mr.
10.
Robinson, why'd you put negatives?
Uh-oh. Negative, negative. Positive, positive. 0, -27, 30. And then 3 times 19 will be 30 and 27. So that's 57. And then our bottom row becomes 0, 0, 30, 30, negative, negative. And again, the point here is so that I can use this -30 to destroy these positive 30s. And now to row 2 and row 1, I will add row 3. Add row 3. And that's going to give us the following. As you go through this procedure, every subsequent step gets faster and faster, because notice this row that I'm adding into the top, since both of these are zeros, it's not going to affect those values at all. So this is still -10, this is still -20, this is still 0, this is still -27. But when I add row 3 to row 2 and row 1, it's going to zero out these entries. So now this is 0, this is 0. The bottom row is unaffected. It's still 0, 0, negative 30. And the thing that it changes, the thing that we have to keep track of, is what it does to the constants. So this bottom one is still going to be negative 30. But if I'm adding row 3 to row 2, negative 30 plus 57 will give us 27. And then up here, up top, negative 30 plus 30 will give us 0.
0.
Is that okay?
Yeah.
Okay. So now we only have a single target left. We only have left this negative 20 that we have to delete, right? And so what I'm going to do is I'm going to multiply row 2 here by 20 over 27. Sorry, negative 20 over 27. And so here's our next step. This is going to give us negative 10, negative 20, 0, 0. And then over here to the left, if I multiply this line by negative 20 over 27, it'll turn it into 0, positive 20, 0, positive 20, 0, 0, negative 30, negative 30. And now to row 1, I'm going to add row 2 plus row 2. And then when I do that, it's going to eliminate this position. And then we'll be one step away from having this in reduced row echelon form. Negative 10, 0, 0, 20, 0, 20, 0, 20, 0, 0, negative 30, negative 30. And of course, all that happened here was I took row 2 and I added it to row 1. So 20 plus negative 20 zeroes out that value. And then 20 plus 0 gives us 20. Now, final step, I'm going to have to multiply each one of these rows. And what am I going to multiply each one of these rows by?
Fraction.
Yeah, what fractions? What do I multiply row 1 by to make it so that the left-hand side is what we need it to look like?
Negative 1 over 10.
We're going to multiply row 1 by negative 1/10. We're going to multiply row 2 by
1/10.
1/20th. And we're going to multiply
1/20th.
row 3 by negative
30th.
1/30th. And so this is going to give us our final answer. The left-hand side has become the identity matrix, which is how we know that we are done. And then on the right-hand side, 20 divided by negative 1/10 is negative 2. 20 divided by 20 is positive 1. And negative 30 divided by negative 30 is positive 1. And so the answer to the question, well, what is the intersection of this system of linear equations? The answer is negative 2, comma 1, comma 1. Are there any questions on this technique or how we arrive at our answer here?
So, Mr. Robinson, the last step is always to make sure it looks like that identity matrix.
Yeah.
So, Mr. Robinson, you're saying that our calculator can do this?
Oh, wait, I'm going to apologize to you. I just caught a small mistake. This is negative and this is positive, and then I multiplied it by a negative number. So this should end up being positive 20. This should end up being negative 20. So then in this row, this is negative 20. In this row, that would make it so that this was also negative 20 because I'm adding negative 20 to 0. So that's negative there. So then in the final step, this is positive 2 and this is negative 1. My apologies. This is positive 2 and this is negative 1. And yeah, your calculator does this. So we're going to go over how to do that. Though, as I will constantly warn you, as some of y'all learn the hard way on the mid-chapter quiz, if you have the correct answer but the work doesn't match, you don't get credit for it. Because we're all taking these exams at home, which means we have access to the internet. And, you know, I could also just type the question into Wolfram Alpha and get the work. So if you were to provide the correct answer here to negative 1, 1, without all of this work come the chapter test, you would get a 0 anyway. So please keep in mind that the point of these calculator techniques is not to do that instead. It's just to make sure that you get the correct answer and that you work towards it so that when you get there in the end, you can know whether or not this is right.
Mr. Robinson, if you don't mind, can you please scroll up?
Like that?
Yeah, perfect.
Okay.
Thank you.
Mm-hmm.
Thank you.
Yep. Okay. And now the calculator tutorial. And then after we go over this, I will like write it out here. But all you'll need for this is the original augmented coefficient matrix. Let me go ahead and start up my graphing calculator emulator just because it's cleaner than showing y'all on my actual factual physical calculator here. Give me 1 second to get that thing started up. Student folders, TI-84, emulator. Okay, share screen. Okay. Now we're in our graphing calculator. Y'all can see that, right? And you can see the mouse.
Yeah, we see it.
Okay. So the first thing that we have to do is we need to enter our augmented coefficient matrix in the calculator. So I'm going to hit second matrix so that we can get here to the matrix menu. And we're going to have to edit one of these matrices to be the same as our augmented coefficient matrix. And so to do that, the first thing that we have to do is indicate to it what size of matrix we're talking about. How big is our augmented coefficient matrix?
3 by 3.
You would think it's a 3 by 3, but we also have to include the coefficients on the other side. So it's actually a
4 by 4.
By 4.
Say that again. It's rows by columns. How many rows?
3 by 4.
There we
3
go.
by
It's 3
4,
by
yeah.
4. Okay, so that's the first thing. Now that we have it entered as a 3 by 4, I'm just going to go ahead and I'm going to enter my values 1 and 2 and -3 and -3. And then it's going to be 2 and -5 and 4 and 13 and 5 and 4 and -1 and 5. Okay, so now that that's entered, I'm just gonna quit out of here, back to the top menu, just because that like saves the matrix. And now if I go back to matrix, we know that it's properly entered because there's a 3 by 4 next to A, which means it saved everything that we just punched into it, right? I just want y'all to know, and this again is why I talk about the vocab of like row echelon form versus reduced row echelon form. I want y'all to know that, actually, I think I can do this. Now I'm sharing my whole screen, yeah? Y'all can see everything?
Yeah.
Okay. Minimize that, okay. What I want y'all to know is that we can get this into, give us row echelon form. We can also get it to give us this, which is reduced row echelon form. The difference between the two being that when it comes to row echelon form, only the bottom left corner is knocked out, but when it comes to reduced row echelon form, the bottom left corner and the top right corner are both knocked out. So here's how we do this. We're going to go over here to our graphing calculator, and we're going to hit second matrix. And then once we're in the matrix menu, we're going to go right one menu to math. And under the math menu, if you scroll down past all the numbered options to A and B, you'll see one option that says REF, and you'll see another option that says RREF. REF, of course, means row echelon form. RREF means reduced row echelon form. So I'm going to pick option A, ref, and then we have to tell it what matrix we're talking about. So I'll go back to the matrix menu where it says matrix A and hit enter. And now when I close the parentheses, it's going to give us the row echelon form of matrix A, which is this. So it's going to be 1, 1, 1, and then these entries here. And if you need to go left and right, you can go left and right. Oops, sorry, I forgot if I click too quickly, it'll snap the calculator to the right. And notice that, what is it doing to the diagonal elements here?
Just making it identical.
It's making it identity. So it's taking the
Identity.
diagonal elements and it's dividing them all so that they are 1. But if you were to do that here and divide by -1, -9, and -11, you would get back this identical matrix. And the sucky thing is that it turns them into fractions, so you'll need to be able to read what those fractions are, right? So what fraction is 0.6666 repeating?
2/3.
That's 2/3. 0.2 is 2/10. 1.66 negative is 1 2/3, which you can turn into a mixed fraction. But here's the more interesting thing, because if you wanted to get, like, if you just wanted the answer, what is X and Y and Z for this system, from here you'd have to do more math, which is why I don't know why you would ever do that unless you just wanted to make sure that this intermediary step was correct. For the most part, what we're interested in is the answer. So if we go over to math and we go to RREF, reduced row echelon form, and then we tell it, hey, yeah, give me the reduced row echelon form of matrix A, and then hit enter. Now it'll just solve it for us. You get the identity matrix on the left-hand side, and then you get 2, -1, 1. 2, -1, 1. Is that okay? A little calculator tutorial there.
Yeah.
Okay. So just
Mr. Olson, can you plug your solutions into the solution? I mean the equation.
I mean, if you took this solution, 2, -1, 1, and plugged it into all 3 of these original equations, they would all return true statements.
That's what I mean. Can you like correct, like test what you're saying if it's test your answer by doing that?
Yeah, of course. So that's what it means for this to be the solution to the system. If you plugged it in here, you would get -3 equals -3. Plugged it in here, you would get 13 equals 13. Plugged it in here, you would get 5 equals 5. Okay. And so here's just like a quick breakdown of how to do that. You go to matrix, and then you enter your matrix. And you have to keep in mind that you need it to have the correct dimensionality. So in this case, since it was 3 variables, it has to be a 3x4, because you also need to give it that set of constants on the right-hand side. And then after you do that, you go back to the matrix menu again, and then you go write one option to math. And then under that math option, there are 2 things that you can do there. Option A is REF, which gets us into row echelon form in case you want to check this intermediary step and make sure that you haven't made any mistakes halfway through your solution. Or if you want to check your final answer, you go to B, to RREF, reduce row echelon form, plug in your matrix, and then it will just straight up turn the left-hand side into the identity matrix for you so that you can immediately read your solution. And that's it for this question. I know that it's time consuming, but it's only because, you know, we didn't do an example of a 3x3. So these 3x3s, time consuming, not terrible, but mostly just because I was talking over it the whole time. Are there any questions up through here? Is this okay? Good?
Yeah. Yeah.
Okay. And now I got 2 little note items for you to add, like just tack it onto your notes, so this isn't super big. I just want y'all to know how to interpret some of the weirder things that may happen while doing this technique. This is, again, 9.6. And we'll just say that this is notes continued. Oh my God, why? Okay. Just so y'all know, here's what to look out for in case we have a case of no solution, and how to interpret it, and a case of infinite solutions, and how to interpret it. So if you are working on this procedure, and for notating this out, I'm just going to do it in a 3x3 matrix just because that's what we were just working on, you know. If you are working with a system of 3 linear equations, which represent 3 planes, and it turns out that there is no solution to that system of equations, which is to say 2 of your planes are parallel, or maybe even all three of them are parallel, it's going to be really clear when you're working on your problem, because you are going to end up in the following form. You are going to get some setup where two of your rows are okay. I have A11, A12, A13. You might have a 0 entry here. This is still fine. A22, A23. And then on the right-hand side, you might have some numbers, some C1, some C2, and some C3. And here's how we know it's no solution. One of your rows will 0 out. Why is this indicative of no solution? What is this bottom equation actually talking about? What does this mean?
That C3 is equal to 0.
Um,
So any given number is equal to 0, which is not possible.
it's not that exactly. So keep in mind that each one of these columns is indicative of that term multiplied by a variable. This first column, if you wanted to turn this back into its system of linear equations, these all get multiplied by x, these all get multiplied by y, and these all get multiplied by z. So here's what this bottom equation is saying. This is saying 0x plus 0y plus 0z is equal to a number. 0 times anything is 0. 0 plus 0 plus 0 is equal to 0. So 0 is equal to a number. Is 0 equal to a number? Is
No.
that possible?
No.
No. So if you are ever working in one of these matrices trying to solve it by elimination, and you end up with 0, 0, 0 digit, that is telling you that there is no solution. There is some sort of contradiction in that matrix. And here's how we know that we are looking at a system that contains infinite solutions.
Mr. Robinson, also for no solutions, there's no way to tell, like, off the bat, you need to do some work first.
Yeah, and you'll hit on it pretty quickly, because once you're like, okay, I'm going to eliminate this dude, when you take the information from these two matrices to eliminate these entries, it will also eliminate this entry.
Okay, I see.
Good. And then if you are working in a case of infinite solutions, it's really similar, which is why I'm doing these side by side. There is a slight difference. The first row will still appear normal. A11, A12, A13, D, and then constant 1. And then you'll get the next row to 0 out. So you'll get 0, A22, A23, C2. And then when you eliminate out these two entries here in the bottom row, you are going to get 0, 0, 0, 0. So here's what this is saying. This bottom equation, that's fine. You could have that 0 times x plus 0 times y plus 0 times z is equal to 0. That's a true statement. So you get 0 equals 0. That's great. But what this is telling us is that there are not 3 constraints. So the reason why you get one ordered pair in physical space, think back to the beginning of the chapter, right? A system of 3 equations represents 3 whats? What kind of mathematical objects are we talking about?
Intersections.
Very,
The intersection of 3 whats, though?
very
Planes.
Planes, yeah.
3 planes, right? So in the warm-up question, we had a definite solution, which is to say, sorry, give me 1 second here. Okay, yeah. Okay. In the warm-up here, we had 3 individual constraints, which give us case 6, right? So all 3 of those planes met at one point, and it just so happened that in the warm-up, that point was the point in space 2, -1, +1, right? But if one of your planes zeroes out, what that's telling you is that 2 of your constraints are identical. 2 of the planes that we were given are actually the exact same plane. So because 2 of the planes are the same, then we're talking about case 2 on this slide, right? Where we have 2 planes and they are intersecting along a 2 planes intersect and they intersect along a line. Yep. So that line is the solution, and all of the points along it are technically the solution of the system, which is to say that the answer then becomes whatever these two equations are. So the answer is all points along whatever these top two equations, whatever information is left over there, which is to say a11x plus a12y plus a13z is equal to C1. And our second linear equation is a22y plus a23z is equal to C2. And if you were feeling like a fancy lad or lass and you wanted to make your answer really nice and clean, you could solve for one of the variables, either y or z, and plug that into the top equation. And whatever linear equation you're left over with, that is the line along which these two planes intersect. This system of equations becomes our area where the infinite solutions exist. And that's it for this section. I don't think it's that much stuff because the math that we're doing is actually the same as elimination. It's just really time consuming to write down all of those digits every single step. This section is not mathematically difficult, like we're literally multiplying numbers by other numbers and adding numbers to other numbers. We're not like graphing or anything fancy, but boy, is it tedious. Difficult in terms of handwriting, but easy in terms of logic. Anyway, we have like 10 minutes left, so feel free to hang out, ask a question, any of that good stuff. Let me make an assignment so that y'all can upload the classwork for this week. And then after that, you know, it's Friday, so you have your other classes, and then you're free to go to the weekend. Like I said, the 9.6 homework is due tomorrow night instead of tonight, just because it's a lot of writing. But if you finish it, feel free to upload it, and then, you know, you're free until Monday. Do we have class on Monday?
Yeah, just Friday we're off.
Yeah, we have next Friday off. That's right.
Mr. Robinson?
Yep.
Since these are mostly time consuming, how many of the would it be 2 or 1 problems on the test?
On the test, because of how time consuming these are, I plan on giving 2 by 2 matrices, and either one 3 by 3 matrix where all of the entries are entries, or a 4 by 4 matrix, so you would be solving for W, X, Y, and Z. But if I give you a 4 by 4, there are going to be so many zeros to start off with, because if I gave you a 4 by 4 to solve from scratch where all of the numbers were numbers, that could be the whole test on its own. Like that could take a good 40 minutes.
Right.
Yeah.
So yeah, if I give you a 4 by 4, and I guess we'll probably do a 4 by 4 for the warm up on Monday. That 4 by 4 is going to look like Swiss cheese. It's going to be mostly holes to start off with.
Right.
Oh, and let me ask you this. So we've had 2 weeks of classwork, right? And then we had spring break. Does that make this week 4, or is this week 3?
4.
I guess if you count spring break 4.
I'm going to count spring break as a week. So yeah, I'm going to make this week 4 classwork. And if anybody asks, hey, how come there's no week 3 classwork? It's because week 3 was spring break. You guys made that decision, not me. Week 4 classwork. Or I guess if I was responsible, I wouldn't even number the weeks and I would just put the dates or whatever, huh? Oh well, 10 points of classwork, and it's due today at 9. Classwork, and then I actually need to take that from every class and hit assign. Okay, great. Okay, yeah, feel free to upload your classwork whenever you have time. There's no, and if you upload it late, there's obviously no